Hello everyone. Welcome to this webinar on real-time simulation and testing using Simulink Real-Time and Speedgoat. My name is Sharath and I work with the sales team at Trident InfoSol. I will be your moderator for today and will take you through this webinar. Just before we get started, I would like to inform our audience that this webinar is dedicated to the teaching faculty, the educational institutes and the research centers. We've been doing a lot of these webinars to the industries, be it automotive, avionics, industrial applications. But this is something very dedicated to the educational sector. The reason being because we're working with a lot of projects on electric vehicles, be it autonomous vehicles or the unmanned air vehicles. We see a lot of potentials with the college research projects. There are a lot of industries who are looking at real-time simulations because real-time simulation or the HIL or the RCP is such a key element with any of the industries today. And that gives a lot of opportunities for the colleges to engage with the industries. And that's the real reason for starting this webinar today. So without further ado, I would just start with my presentation today. So the agenda for today is I would just be walking you through some of the introduction, what exactly we are planning to do with this session today. And in the later part, you will have our speakers talking about the concepts of hardware in loop and the rapid control prototyping using Simulink as a platform there. And we will also be talking about our Speedgoat hardware, which is the real-time target machines, which will be used to deploy your models that you develop on Simulink, deploy on these hardware. And we have some interesting demos towards the end of it. So stay tuned. And for the question and answers, you can write your questions anytime during the webinar. Currently, everybody is on listen-only mode. So towards the end of the session, we will be taking the questions. So right then, so Trident InfoSol, we started our operations in the year 2000. So we are completing close to 2 decades of operations. We have offices across India. And in the industry, we are known as an embedded solutions provider. So that's what Trident InfoSol is known in the market. These are some of a partial list of clients that we've been working today. This is not an exhaustive list. These are some of the lists that I had to pull out. We have our defense customers that you see on the left. In the middle that you see as our corporate customers, large companies, large automotive customers. And on the right is some of the educational institutions that we have already worked with. Again, as I said, these are some of the small lists of customers that we are working today. Coming to the business verticals, Trident, we have 3 major verticals on the COTS hardware, COTS software, and the system solution. Let me quickly walk you through that. The COTS hardware is a division where we have a lot of readily available hardware, be it a single board computers, that go into avionics and other high-end applications, or maybe some mezzanine cards or the daughter cards or IO expansion cards or whatever you call them. So these are some of the other things that we cater to. And here you see a list of companies that we work with on the hardware side. So these are the companies that are providing us the hardware solutions. The commercially off-the-shelf boards that I was talking about in the previous slide, these are the companies that are providing them. And moving along, this is the software group, the group that is in fact responsible for organizing this webinar today. So if you really typically look at any product development in industries today, they follow a typical V cycle. So the left that you see, the left end and the right end that you see are the companies that we work with. In the middle of the products. So if you start with any product development, it starts with gathering your requirements. So we have solutions that help you with the requirements management, and then you have some model development tools, be it what we talk about Simulink and all these tools that help you design your models. We also work with some embedded code development tools. And moving along, there are a lot of testing that comes into after your development. So we work with some of the test tools. And then the real key thing comes in with the hardware and loop simulation. So we are talking about Speedgoat today. That is a webinar. That's what Trident typically works with. So Trident has been working with Speedgoat for quite some time now. These are some of the companies that we work with the software group. So Speedgoat is our focus today. So we will be talking about Speedgoat. And this is our final group. Here is where we develop a lot of products, Trident in-house. We make a lot of these hardwares. Again, that goes into a lot of defense, avionics applications, automotive applications. So all of these that you see are in-house developed at Trident. And these are some of our capabilities that we have in-house, a lot of test facilities that we have within Trident. And so that brings to end of my slide. All I recommend everybody is to follow us on YouTube and LinkedIn, because we do a lot of webinars every week, every fortnight, spanning across various technologies. What you're hearing today will also be uploaded here on YouTube and LinkedIn. So find us on LinkedIn and YouTube, and you can search for Trident InfoSol and just follow us along. A copy of this presentation will be recorded, including the demo that you see towards the end, and will be shared across in the email to all the audience present here today. Right, so that now brings me to the interesting part of today's webinar. So I would like to introduce our first speaker for today. He's Mr. Naga Pemaraju. He works with MathWorks. Naga has experience with working with customers. He typically works with customers, helping them adopt model-based system design, especially using MathWorks tools, Simulink, MATLAB. He has worked with various industries, be it aerospace, automotive, all the domains, you name it. And he also holds a master degree in electrical from the Texas University. I think with over 13 plus years of experience, Naga would be the right person to talk about the model-based system designs today. So he will be talking about the first part of the presentation. Moving along, I have Ms. Spurti from Trident InfoSol. She has over 3+ years of experience, and she comes with, again, experience on model-based designs, integrating them on the real-time target machine, because once you come from Simulink, you'll have to go into the real-time platforms. So Spurti will be helping you understand what kind of specs and what kind of hardware we have, just to understand that part. And finally, we have Dr. Christoph Hahn. Dr. Christoph Hahn, he's been working with Speedgoat. I mean, just to talk about his expertise, he specifically comes from the group that helps a lot of colleges across the globe. He has been helping these colleges in their R&D efforts, mainly in the areas of, I mean, not limited to these areas, but mainly in the areas of automated driving, model-based design for full vehicle, or it could be the control design for these vehicles. So that comes as major experience. And he's got some real interesting demo to show you all towards the end. A good example on the motor kit. Again, motor is such an important part of electric vehicles today. So Christoph will be talking about that. So right now I will be handing it over to Mr. Naga from MathWorks. And again, just one last thing, you see a lot of companies here, MathWorks, Trident, InfoSol, Speedgoat. Our speakers today will help you understand how all of these companies work in an ecosystem, helping our customers, deploy those complex technologies. So over to you, Naga.
Hey, thanks, Sharath. Good afternoon, everyone. Thanks for attending this webinar, and thank you, Sharath, for the introduction and inviting MathWorks for this call, for this webinar. I am here to talk about the real-time simulation and testing with Simulink real-time and Speedgoat hardware. I am Naga Pemaraju, application engineering from MathWorks. I work out of Hyderabad office, and I mainly support customers across domains, helping them with modeling, simulation, and controls. So quickly moving on to the topic. The first question I ask everyone is why real-time simulations, right? So we know the topic itself says real-time simulation, but why real-time simulations? To answer the question, so typically in the industry we do see a lot of fatalities happening. In this case, a big machine being blown off because of some glitches in the software as well as hardware. So and this could be one area of risk which people are working, especially if someone is working in the area of electrical systems or power systems, etc. And there might be some very huge systems like the one you see in this screen, right? So these kind of systems are very very humongous, and it's very tough to understand how things are working, test them, and then finally make sure it's working on the expected lines. So these are some of the challenges with such kind of a system. So, and the other part why industry is focusing on real-time simulations is because of the whole in the project timelines that takes place, and how can we actually test it. So it starts with the requirements, make sure you deploy the code onto the embedded target, and finally test and verify it, right? So it's a very big cycle. So how can we reduce the cycle? So the answer is real-time simulations helps in all of these aspects of it. It mainly helps you to test your software against the hardware and make sure you can test all kind of functionalities as well as failure mode scenarios, and make sure your software is bug free before you move to the final integration and test phase. So that brings me to the the V cycle which Sharath was talking about. Maybe I'll just go a little bit deep inside this. So this is a typical V cycle which people follow across the industries. So on the left side of the V cycle is mainly for the design and development. On the right side of the V is mainly for verification and validation. So on the left side, typically people starts with requirements, and once you have the requirements frozen, you do the system level design, and then once you understand and uh, freeze on that system level design, you get onto the subsystem level design and finally implement, right? So that is on the left side, but once you implement it, you need to make sure it is working fine. That's when you do the testing at each and every level. First at the subsystem level, next at the complete system level, and finally at integration test phase with the actual system. So where exactly this real-time system can be done in this particular recycle? The first thing, we do this real-time simulation and testing at the system level design phase, right? That is what we call this process as a rapid prototyping. And the second one is mainly at the system level integration and test phase of what we call as a hill testing, hardware in the loop simulation and testing, right? So these two are the main areas in the V cycle where we typically do the real-time simulation. Let's try to dig a bit more into these two process. What do we mean by rapid prototyping and hill testing? Starting with rapid controls prototyping. So this is a typical controls architecture. Anyone working on the controls area or working on the electrical or mechanical systems might know. So you have mainly two systems. One is a controller, the other one is a plan model, and you have a feedback coming out of the plan model and given as a feedback to the controller here, right? So this output of the plant is given as a feedback to the controller. So now in this particular architecture, is a typical controls architecture. Uh, we use something called as a real-time target, in this case an embedded controller hardware, on which and we have and we have a real hardware prototype, right? For example, if I'm working on motors, I have a real motor. Now in my model I replace my plant model with the blue box you see is called as IO output and IO input. These are the driver blocks which helps us to communicate with the real hardware. So the whole model, my controller along with the driver blocks are deployed onto this embedded controller hardware. In this case, it's a target computer for us. And then finally, you try to communicate between each other. So as we have discussed earlier, rapid prototyping falls on the left side, right? So in this case, my controller is not yet matured enough. I'm still tweaking with my controller gains and algorithms and features, etc. So it's not yet matured enough to be deployed onto a real embedded target like a DSP processor or an FPGA, right? So that's where this process will help us to tweak the model directly connecting with the real hardware like a motor, and then fine tuning the gains. This way we can, we'll have more confidence on our controls algorithm and features, and then we can actually, get onto the process of deploying onto the DSP. The second application use case is the hardware and loop simulation. Again, I'll come back to the same architecture of a controller and a plant model. Here, I have my controller is matured enough. If you remember, the hardware in the loop simulation is on the right side of the V cycle, right? So by this time, my controller is matured enough. That means it has already been deployed onto a DSP or an FPGA, and it's like one step closer to getting it integrated into the real system. So it's like a final ECU, what you see in this case, right? So in our model, we try to replace the controller with the again driver blocks that helps us to communicate with the ECU. And then finally, the whole model, the plant model and the controller is deployed onto the target computer hardware. And now both of them can talk to each other, which helps us to test different various functionalities or do various failure mode simulations. So this is what we mean by hardware in loop simulation. And this is gaining more prominence across industries because nowadays, a lot of our systems which are working on getting more complex. And for us to make sure these systems work fine, we need to do a lot of verification validation. That's where a lot of these automotive companies or aerospace companies or even companies in the area of industrial industrial domain, industrial automation domain, are getting into the hardware loop simulation and testing, make sure their algorithms are all tested properly before they integrate in the final system. So here is the solution, what we'll be discussing today. Mainly, as you have seen from my earlier slide, there are three main parts to here, where one, you have a development computer where you develop your algorithms and model. Typically here in this case, we are using MathWorks tools to develop your model. Once you develop your model, we need to deploy that onto the target computer, the Speedgoat here. And then finally, once you deploy that onto the target computer, we actually connect to the physical system and do it. So in today's talk, I'll be focusing on the MathWorks, what's the role of MathWorks and how, what kind of work we can do here in this, where do we come in this particular solution, followed by Spurti will be talking about some of the hardware related aspects of the Speedgoat hardware. And then finally, Christoph will be talking about Speedgoat as well as how do you test in the holistic scenario. All right. Again, just one more slide, just giving you an understanding of how this solution works. From the MathWorks side, we, all the MathWorks tools like MATLAB, Simulink, Simscape, all the tools which you can think about are provided from MathWorks. And we do have a flagship product called as Simulink Real-Time, which helps you to take your models, Simulink models from desktop to real-time. And these models can work seamlessly with Speedgoat real-time target machines. Speedgoat provides all the different I/O modules and also provides a protocol support. They provide the driver libraries for us to integrate with various systems, and also they do have FPGA based solutions. So the link that is between MathWorks and the Speedgoat is the kernel, what we call as a real-time operating system that is provided by MathWorks. So this RTOS kernel is from the Simulink Real-Time, a tool from MathWorks, which works exclusively with Speedgoat hardware. That completes the whole solution for anyone who is working in the area of real-time simulation and testing. Here I want to bring a user story from Supergrid Institute from France, who used MATLAB, Simulink, and Speedgoat products for rapid control prototyping of the DC to DC converters, and they were very successful in this approach. Of course, we'll share this link, the slides with you for you to go around. But if you have any questions on this, we encourage you to either visit mathworks.com or speedgoat.com for more such user stories, or you can also reach out to us. And again, in this solution for India, Trident Infosol are the main distributors of Speedgoat, and they would be the face of Speedgoat in India. They take care of all the business aspects of it. Okay, moving on, let's focus on the MathWorks part of this particular solution, right? So as we are talking about MathWorks, as most of you are aware, MathWorks is mainly into modeling and simulation. Main are MATLAB and Simulink models. So we try to work on the models and we try to see come up with an algorithms for controls and connect with come up with algorithms or models for a physical system, do a complete simulation in the desktop area and see how things are working. So here is a model, because the topic for today is PMSM. I thought I'll show you one example on the PMSM controls. Here is a model on PMSM motors using field-oriented velocity control approach, right? On the screen, what you see, the blue one is a controls algorithm, and the right side we have model the complete motor and load. If I quickly move on to the model, let me show you the model. This is how the model looks like. For the people who are new to MATLAB Simulink, so this is a Simulink window where wherein you can do all various kinds of modeling approaches, either you using the first principles approach or using the physical modeling approach, right? And this is a tool which can be used as a system level simulation, mainly used by customers in the system level simulation. So getting into the model, so as I said, this is my controls algorithm and the right side is my plant. So if you remember the architecture I talked about, this is a controller and this is a plant model. So if I just get into the plant model, this is mainly a motor and load which we have considered here. As you can see, we have modeled the PMSM motor, permanent magnet synchronous motor, and these are the blocks which are used from Simscape electrical library, wherein you can just directly feed in the all the parameterization based on your specs, and that can easily help you to represent a motor. So we need not worry about building a PMSM motor from scratch. At the same time, you can also integrate with various peripherals, and you have an inverter model, and you have various again subsystems helping you to do the currents and voltages, right? This is on the plant modeling side. Coming back to the controller, again, as we are talking about the field-oriented controls, there are a lot of subsystems in the field-oriented control, wherein on the left side, what you see is a mode scheduler based on basically it's kind of an high level controls or supervisory controls, which helps you to determine whether you need to run an open loop controls or a closed loop controls, or it's a velocity control or current control, because based on the mode of operation, and you need to switch between some of these controls. So this determines that, and we have in detail controls about either velocity control, current mode, or open loop control. I'll not be getting into the details about it, but the idea is to give you an idea how in one single framework we have modeled controller as well as my complete plan model, in this case motor and loads, which are in which were modeled using physical modeling approaches using Simscape and Simscape electrical, right? So once you give some kind of an inputs, we can simply run the simulation and actually monitor and see the results, how things are working. In this case, uh, the topmost one, you're actually monitoring the mode, as well as, sorry, the topmost one, we are actually monitoring the velocity commanded versus actual velocity, and the mode of operation, and then finally here you're actually seeing the currents, right? As you can see, we have initially moved from standby to encoder index to finally we have calibrated the encoder, and then here you can actually see at around 1 second we are actually meeting the command versus velocity, and then we are able to follow the commanded signal, right? This is how we do a simulation. So this is straightforward. I mean, for the people who are already in the modeling and simulation, this is good. One message I want to leave with is, once you have good modeling aspects, it's easy for us to take to real time using MATLAB Simulink approach and Speedgoat, right? Using these tools, it is easy for you to take it to a real time. Now let's try to see what are the steps involved for us to move from desktop to real time, right? If I just quickly move on. The first step, okay, now that I have made my model, so you are in the desktop world, I need to make sure my models are Simulink real time, they are real time ready. That means first, if you're in the continuous mode, you need to first discretize the model, right? Once you discretize the model, then you need to slice the model into controller and a plant, because controller will go on to one piece of hardware, plant will go to other piece of hardware, right? So that's one of the key things which we need to follow. And once you do this step, the next part is to set up the communication between the controller and plant. Now that we have split the model into two, if it requires some kind of analog communication or digital or various kinds of a protocol support like CAN, LIN, or any other kind of communication is required, that's when we need to make sure all of these communications are established properly. And then finally, once you generate the code for both plant and controller, right? So based on whether you're doing rapid prototyping or hardware loop simulation, you do need the code for both of them, and then accordingly you'll deploy to the target computer hardware. Then finally you simulate, right? These are the steps involved, and how do we move from desktop to real time, and how can we fast track? remember we were talking about some blue boxes in our presentation earlier, talking about rapid prototyping and hardware loop simulator, where we need the IO driver blocks. So these IO driver blocks are provided by Speedgoat based on the configuration we choose for the hardware, right? This will be discussed in detail by Spurti and also by Christoph at a later point probably. Then once you actually model, you make the model real-time capable, you build the model. Once you build the model, you automatically generate the code, you compile the code, and you create an executable like ML.datex file which runs on the target computer machine. Right. In this case, it's a Speedgoat, and using the Ethernet communication, we run this on the target computer, and you can actually monitor how it is working from your computer, from your desktop computer itself. And it's easy. The main idea is you can actually tune various parameters in your model from your Simulink window, and also monitor how your signals are looking in the Simulink data inspector, signal data inspector, and then monitor it live while running in real-time simulation. And as I said, it has a very seamless integration with Simulink. You can, from the Simulink itself, you can run your models in real time without the need for any third party, any other tools. Of course, you can also have your own, create your own tools, which I'll come down to. The whole idea is, from the same model, you can actually tune the signal parameters just like how you do in desktop simulations, and then monitor your signals, and then you can also compare your simulation results on desktop versus what's happening in real time using Simulink Data Inspector. That's the biggest advantage you're getting with this kind of solution, because people working in this area find it a lot of difficult to understand why is it something behaving in one way in the desktop versus what's happening in the other way in the real time. As I said, it also has seamless MATLAB integration. Using MATLAB App Designer, you can create your apps, right? And this apps will help you to talk to the Speedgoat hardware and application running on the Speedgoat, and you can easily tune your, fine-tune your parameters, and also monitor the signals and see how your application is running. So it's like one solution you can think about. It's like one complete solution which provides you all kinds of needed handles to run your real-time simulation. Finally, when someone is interested in doing some kind of a testing, especially they want to get into the automated testing, they could make use of Simulink test from MATLAB Simulink in a product portfolio, where they can create their tests and then execute it on the target computer, and then see how things are. They can create as many test cases as required, and then automatically run this. So this way, you can author your test cases, you can monitor the test performance, and then finally it generates a report for you to see how my tests are performing. So that's that's a very good way of test automation using Simulink test. So let's take a use case of electric motor here. Again, the two things I want to talk about: electric motor for using as a rapid control prototyping, as well as hardware in the loop, right? So if one of the main criteria for us to do motor simulations is the closed loop sample times, right? In this case, if your sample rates around 20 to 30 kilohertz, then typically we run our controller. As we said, this is mainly for rapid prototyping, where the controller is running on the Speedgoat hardware, and you have a real motor which you are integrating with. So the controller of our for the motors is running on the Speedgoat hardware using Simulink real time, and because we are running we are not asking for a very high sample rates, we can make use of the existing IO blocks, IO cards from Speedgoat, which for us to communicate to do ADC or PWM or any other kind of a communication with the hardware and the test. In this case, hardware and test will be a real motor. Whereas there might be a requirement where you need to move to a very high rate of 1 megahertz. That means I'm getting into the more details of my controller, splitting between a CPU and FPGA. right? So that means some of my control loops of which are running at a higher rate can run on my CPU, but for some which needs to run at a very fast rate, for example current controls, we try to make use of the FPGA. Again, we do have, Speedgoat do have programmable FPGAs. You can actually model your model. You can actually model in Simulink and deploy your algorithms directly onto these FPGA cards using the HTL coder. So we have a very good, HTL coder workflow which helps you to complete the process. So within within one single environment, you are doing an end-to-end simulation, deployment, and testing. Now, if you go to the hill simulation, again, electric motor for the hill simulation, as the name indicates, for the hardware loop simulator, the controller is matured enough that it's already deployed onto, say, one of the DSP or an FPGA or an SoC, right? In this case, my hardware and under test will be a finalized controller running on DSP or an FPGA. So then comes my plan model, which needs to run on the Speedgoat. So again, if we are running at a sample rates of 20 to 30 kilohertz speed, our plan model will be running on the CPU part of the Speedgoat hardware, which communicates with my controller using the various PWM captures or DAX board available that Speedgoat provides you. Whereas if you need to do simulations or at faster rate, that is maybe up to 1 megahertz, we will be again making use of the FPGA boards available with Speedgoat, and then you can actually model the algorithms and directly deploy them onto the FPGA boards using the HTL coder workflow. So this is one seamless solution for you. Here is a very high level flow of how you can take your model from modeling to deploying onto the FPGA and finally integrating with SLRT solution. So you create an FPGA model, you design your algorithm in Simulink using the HTL coder workflow. You actually generate the HTL code and run it, integrate with the rest of the real-time model that needs to deploy onto the Simulink real-time, and then finally you deploy it into the Speedgoat hardware. If you have any questions in this region, if you have more interest, please reach out to us. We'll be happy to work with you and take it forward, and we'll be happy to help you in this case. Before closing, I just want to introduce you one of the recent products on motor control Blockset. In 2020, MathWorks has released an exclusive toolbox on motor control. So in using this, you can actually design, implement all your field-oriented controls for PMSMs. We are starting with PMSMs. Of course, we'll be increasing to this facility or this to other motors as well in the coming releases. So we provide a lot of reference examples, and of course you can build FOC algorithm using Park, Clark, and various kinds of controllers, and also you can generate optimized code, embedded code, right? So the blocks available in this are also works with Speedgoat, so I do encourage you to look into this. This can provide you as like a one-stop solution for the whole. Other key features of this motor control block set includes, of course, code generation. You can do the sensor decoders and observers. Other key criteria I want to emphasize in the motor parameter estimation, as you can see in the below video going on here. You can actually connect your system to the motor and actually understand what the actual parameters are, like what's my resistance, inductance, back EMF, and everything. So it will directly measure from the motor, right? You can do the controller auto tuning. We provide various plant models and also reference examples. I do encourage you to read a lot of our resources in this area, mainly on the real-time simulation and testing. It's a detailed document technical article available on MathWorks page. Again, there is an ebook on brushless DC motor controls. I would encourage you to download and start making use of this. These are all technical documents. And finally, a white paper on hardware loops testing for power electronics control design. by both MathWorks and Speedgoat. We have come we have come across this white paper. We have made this white paper for the people working in this area, because this is one of the key, there are a lot of key requirements for us to do hill testing, especially for power electronics. And all the nitty-gritties have been very much explained in detail in this white paper. I would encourage you to get into, download this and read this. Thanks for patiently listening to me. That's all from my end. Now I'll hand it over to Spurti to walk you through the hardware, and she will walk you through even more details about the Speedgoat and what different IO cards are.
Thanks, Naga. Thanks for giving a detailed explanation about motor control model and also the details of Simulink solutions for real-time simulation. In the next few slides, we are going to see what are the products available from Speedgoat as a hardware partner in order to carry out real-time testing and simulation. So whatever the models you have in your Simulink, if you want to take it to RCP or hardware in the loop simulation, then definitely you need target computers. So we offer, or Speedgoat offers, different type of target computers. So the first type of target computer is unit real-time target machine. It's a small one, lightweight, and also a rugged computer which offers connectivity for multiple IOs, multiple input-output functionality. So here the CPU is Intel Atom CPU. It has a 4 GB RAM, and also it has a slot of one MPCIe slot for the connection of IO modules. So what you are seeing on the screen is unit real-time target machine. Here, by default, you are going to get some of the connectivity functionalities like Ethernet, USB, and also if you want to connect to the monitor, then you will have a provision. With the help of one slot of IO, you can have multiple functionalities like analog, digital, or even some of the motor control signals like PWM generation or PWM capturing, and also for the encoder feedbacks. Coming to the communication protocols support for unit real-time target machine, we can have all the automotive protocols like CAN, CAN-FT, LIN, and also some of the customized protocols like SPI and also I2C. So the key feature of unit real-time target machine is you can run any of your real-time application which is created in Simulink, and you can also achieve the sample rates of about 20 kilohertz with the help of FPGA IO module. I'll give you details of the FPGA card later in my presentation. So the next target machine is baseline real-time target machine. Here, it is also a smaller target machine which provides IO support for diverse functionalities. So here there are two variants. The one is baseline yes, what you are seeing in the first two images, and baseline YUM, the third one. So the CPU here is Intel Celeron, and as I told, by default you are going to get connectivities like Ethernet, USB ports, and also serial ports. We have option of including 4 IO modules for the baseline real-time target machine, and in case of baseline M, you can have up to 6 IO modules. So here, if you are preferring for start your real-time testing from a smaller application or with a limited number of IO functions, then preferably you can go with baseline real-time target machine. The third type is mobile real-time target machine. If you wish to take your target machines for the vehicle testing or on-field testing, then the ideal one is mobile real-time machine. Here, it offers Intel Core i7 CPU as well as FPGA cards. So we can have option of adding 7 number of IO modules, and also we can go up to 14 number of IO modules. So what you're seeing on the slides are 3 different types of the mobile real-time target machine, where the number of possible IO cards that you can insert on the machine are different in each of them. The higher end target machine from Speedgoat is performance real-time machine. So when you are looking for running your models at a much higher sample rate, and also if you have multiple IO functionalities or multiple IO cards, then we can go with performance real-time target machine. Here again, we can have by default we can have Intel Core i7 CPU, whereas if you require a higher end of CPU, then there is also a possibility to go for Xeon CPUs. If you are wishing to run your model or your part of the model on FPGAs, then we can have both CPU as well as FPGAs. So here by default there will be option available to include 7 IO cards. Whereas if you require more number of IO cards for your application, then we can have an expansion chassis, which is shown in the right side of the slide. So you can connect the expansion chassis for the main target machine in order to increase the number of IO slots. And both of them will be connected through a InfiniBand cable. So both the machine will act like a single machine. It will be no longer like 2 different boxes, but just like a single machine. Here, the performance machine is also more suitable, or when we are going for the rack setup, where we can install up to 100 number of IO modules. So we can also have signal conditioning or any of the other requirement like breakout. You can take out the wires from or the signals from your target machine, and you can go for connecting it to CROs. So complete for the rack setup, we can go with the performance real-time target machine. So in this slide, I just want to quickly show you the setup, how we are going to make when you have Simulink and real-time target computer. So the first part is development computer, where you will have all your MATLAB toolboxes, including MATLAB, Simulink, and also the coder products. And then you will have the target computer from Speedgoat. The target computer will include the CPU or FPGAs and also Simulink real-time kernel, and also the IO cards. So the connection between development computer and the target computer will be through Ethernet cable. So Simulink real-time kernel is a real-time operating system which is dedicatedly made for the Speedgoat target computer. So Simulink real-time will help you to take your model from desktop simulation to the target computer or real-time execution. So the target computer will be connected to your device under test or any of your physical system that you want to test with the help of the IO cards. So this will be the setup when we are having Simulink as the development platform and Speedgoat as the platform for real-time simulation. So there are some of the MathWorks toolboxes are required in order to use our target computers for RCPO. The first one is Simulink real-time. As I told you, Simulink real-time is a real-time operating system in order to run your models in real-time. Then MATLAB Simulink, MATLAB coder, Simulink coder. So Simulink coder will help to automatically generate C code from your Simulink model when you're taking your model for the Speedgoat hardware. And at last, it is HDL coder. HDL coder is required to generate VHDL or the hardware description language from your Simulink model and run it on the FPGA. So only if FPGA card is involved, then HDL coder is required. Otherwise, we can go with just with the first 5 toolboxes. Here is a list of I/O modules and communication protocols supported. Almost all the communication protocols and I/O functionalities are covered by Speedgoat. So it can be starting from the analog, whereas we have different cards which has both provision for analog input and analog output. So the number of channels or the resolution can be different in different cards. So we offer multiple cards based on the requirement of your application. Then we can choose one particular card. And we also offer separate digital cards which support different voltage levels like TTL, or even we can have transceivers of RS-232, RS-422, or the voltage levels of LVDS. And there are some of the cards which FPGA cards preferably to implement functionalities like PWM signals or encoder signals, and also the protocols like I2C, SPI. All those functionalities can be executed on FPGAs. For the relays, we offer different type of switches based on number of channels that would be required. And also we have cards for fault insertion, where you can deliberately insert connect to the ground or shorting of the two signals and see how the system behaves. So you can simulate different type of fault scenarios in real time. And there are also cards available to simulate battery behavior in battery management system. So on the battery simulation card, you can actually simulate the battery behavior. You can also measure the battery temperature, battery voltages, and you can use it for hardware in the loop simulation of BMS. So these are some of the I/O card supported from Speedgoat. I'll also show some of. Sorry guys, I was lost in between. So here we are seeing one of the analog I/O module, IO133. It offers analog inputs of about 16 channels, whereas the resolution of this particular ADC is 16-bit. So it offers the voltage ranges from plus or minus 10 volt and also plus or minus 5 volt. Whereas we can select this voltage levels in Simulink platform itself. So it supports a simultaneous sampling of the input signal. And there is a provision to select between the voltage levels in Simulink itself. So there are also 14 digital TTL lines available. So individually, the input or we can make a signal as input or output on the software itself. So this is a specification of an analog IO card, IO133. I also want to share details of one of the digital IO module. So there are, again, as I told you, there are different IO cards available for the different channels and also the different voltage. So here is one particular IO card, IO204. So it supports basically two type of voltage levels. So in case of digital input, we can have an option of either 24 volt or 12 volt. So for both the type of voltage levels, the number of input signals that you can send are 16 channels. And each of the channels are galvanically isolated. And there are also 16 digital outputs available the voltage levels on these signals will be between 6 to 48 volt. So these are some of the cards that I have took for presentation. Maybe based on the requirement of the application, we can have different IO cards. So we provide a vast number of cards based on the voltage or the number of channels. So the IO613 is the CAN IO module which is dedicatedly available for education. So here, this particular IO module offers 2 CAN ports. So either we can set it for CAN fixed, CAN FD or CAN high speed. So the selection of the between these support for CAN FD or CAN high speed, we can make it on Simulink itself. So for each of these type of IO card, there will be a driver block given by Speedgoat only. So you can place those driver blocks in your Simulink model and make the configuration based on the number of channels or the voltage levels, or for the protocols like CAN, you can switch between CAN high speed, or for some of the cards it can also be link. So these are some of the fixed functionality IO cards or analog input or digital card. So in next few slides, I want to show our solution for FPGAs. Suppose if we are dealing with the power electronics applications, then these type of application demands higher sampling time, or or the very low, higher sampling frequency, or very low sampling time, like from microseconds or nanoseconds, and the latency should also be very less. It also requires floating point support. So if you have these kind of Simscape models or the Simulink models, then we offer FPGA cards in order to meet these type of requirements. Suppose here you can see I have just taken a one small example where any of your power electronics application which require a very small time step or a very higher sample rates. So you want to capture the signals at very fast rate. So for these type of signals, it is not in seconds but in millisecond, and for some of the application it can also be in microseconds. So for these type of very small time steps, we have FPGA IO modules available. So there are two types of FPGA cards supported. One is configurable FPGA IO module, and the second one is programmable FPGA IO module. So the configurable FPGA, we can go for the sampling frequency of around 20. Go up to 1 megahertz from 20 kilohertz. So let's see what is the difference in terms of workflow for these two FPGAs. So in case of configurable FPGA IO module, the IP core or bit stream, we usually call it as code module, or in simple words, it is the IP core for the FPGA, will be given by Speedgoat only. If you give your requirement, for example, we want so many number of channels of PWM signals or so many number of encoder signals, then the bit stream will be provided to you, so that you don't have to worry on programming of your FPGA. You can directly add this bit stream into your model and then start using the FPGA just like any other IO card. You don't have to really worry on the coding part of the FPGA. So this is the configurable FPGA workflow. And if you want to change your functionality, then we can also at any point of time we can give you the different bit stream for your FPGA based on the requirement of your for your application. So the second one is programmable FPGA. As I told you, this can be used when you want to achieve very higher sampling rate, and also you want to code your FPGA on your own. Again, coding in the sense you don't have to write anything here. Once you have done with the Simulink model, then you have to go with the HDL coder workflow. There is also a HDL coder integration package which is dedicatedly available for Speedgoat hardware. So you can decide which particular block of your model, for example, any particular block in your model requires to run on FPGA for achieving higher sampling rate or sampling frequency. Then you can decide that particular block and you can go with the HDL coder workflow.
Hi everyone, sorry for the inconvenience. There is some network issue. We'll do one thing. We'll have Chris to give us demo right now.
So what I additionally do is sharing my webcam, which supposedly should give you sight to some hardware. So what you currently see here is and I'm pointing to that with my blue pen, is a Speedgoat baseline equipped with a few I/O modules, 4 of them, which are attached at the background. And what we have on top of it is the electric motor control kit. The 2 cables here are connected with an FPGA module. I'll explain in a minute why that is. This is a 3-phase motor, DC motor, which is powered from this inverter module. So the blue box at the bottom is an inverter module, which we call power module. The motor receives the power from the power module, and also the sensing commands from the motor go back into the machine using these cables. I'll in a second show you what this demo can do, but before I want to give you a quick glimpse into where you can all get this. So if you please follow your attention to the screen. So I've put a web page on my screen which explains all the details about the electric motor control kit. Especially if you're interested in the specifications, you will find all the details here. What kind of motor it is, what the power range of all the components are, what the capabilities are. So find anything relevant on this webpage. If you have questions, there's always the opportunity to connect Speedgoat people, or in India it's Trident that will help you there. I'll also show you a second web page before I move into MATLAB directly, because everything I'll be showing you in the next few minutes is available on the Speedgoat web page as well. So if you follow that link here and download files, you will receive anything that I will be showing in the next step of my presentation. So find here a holistic overview about what you can do with a motor control kit as well. So now let's move into MATLAB right now. If you download the motor control application, so you will basically receive a nicely packaged zip with the entire project here. So it will come with a nice documentation. So that is here on my screen. It really guides you through every step how you can run the demo. So, and I will do the same. There's a part which is called model in the loop. So this is hardware independent, but it's a great environment for the left part of the V cycle where you set up your controller, where you set up your motor. Then you immediately can go into the rapid control prototyping, which I also show you. And there's much more to the V cycle when you get started there. So this is basically what I'm going to do now. So I will open the model in the loop example. And this is, you will remember Naga's presentation, and so I will not go into the details at all. Here under model, you will find a detailed model of the electric motor itself. So it's a PMSM motor, which is modeled using the SimScale language. At the same time, you have the field-oriented controller here. I'll absolutely not go into the details because it's much more interesting to look at the hardware, and Naga has done a perfect job in explaining you this. So let's go together to the RCP part of the model, which is here. So you will immediately see one difference. The right part here is not a model anymore. It's a photo of the hardware. But what does it mean? So let's go inside this block. And what we immediately will see, and both Naga and Spooty have talked about this, and we will see the I/O blocks. So let me just click on one of these I/O blocks. Yeah, this is the setup block, but let's go, for example, into the PWM generation block. So this block talks actually to the FPGA module, and we will all agree that PWM signals are in the microsecond or sometimes even nanosecond domain, so you need a very quick execution for these pulses, and this requires really powerful hardware, and in our case, we are using an FPGA for that. Yeah, sure. The FPGAs, in summary, are there to cope with the required pulse frequencies in the megahertz domain. What Naga has also mentioned, so let me only briefly go through that. If you go to the library, the Simulink library, you can navigate down to the Speedgoat library, and just for example, you will find your dedicated I/O module there if you want to check it out. I know that we are working with the 3907, and you will find many blocks, as you've seen already, for the PWM generation or capture, and as Booty has nicely introduced, many more for analog signals, digital signals, and so on. So this is as easy as you can integrate a Speedgoat hardware into your Simulink model. It's just getting the library, installing the library, and then you have all the blocks at your disposal. But enough said, let's try to run this demo. And coming back to another point that Naga has already mentioned, there's App Designer, and the apps are basically a very nice way to control applications like the motor control application. So without further ado, I will start the application. And what you will see in the webcam again is the motor is spinning. I hope you also can hear a tiny little noise of the motor. And it is really as simple as that. I can use the app to change the spinning speed of the motor. I go back to a very slow motor execution. In the bottom window at the bottom right, you can actually see how the controller nicely follows the trajectory of the motor. And this is basically how easy it is to get the motor control demo running. I've given you all information how you can access this motor control kit, how you can download the application, and that's up to you, the organizing team. If you give me 2 or 3 more minutes, I'd be ready to show the data inspector as well as how the field-oriented controller works. If we are already out of time, thanks very much for paying attention, and I think then we can open to questions from the panel. But I'm happy to go into some details if desired. So what I'll do is I'll just continue talking, and you can always mute me or take the presenter privileges from me. Let's open together the Simulink simulation data inspector. So in case we are really interested in the detailed signals that the motor is getting, we can look into the commands themselves. So for example, the phase currents. So let's plot both of them, and they are closely related to the control itself. So if we change the motor speed, we will immediately see a different amplitude, but as well as frequency. So if we zoom in a bit more into this signal, we will see why PWM generation from a powerful FPGA model is required, because otherwise a CPU would not be able to cope with the megahertz requirements regarding PWM generation. So this is really a key thing here. Yep, and just bringing you back to the MATLAB screen, with this reference application, you have a full-fledged overview, so you can start it. You can get started right away. You have the documentation available. You have the user interface app. You can even work with your own motor control kit if desired. You have a model in the loop, so simulation only workflow, and a rapid control prototyping workflow. So I hope this was interesting for all of you, and now I'm giving it back to the organizers for the Q&A session. Thank you.
Thank you, Dr. Chris.
Ashar, can you repeat the question? Sorry.
Yes, the question was, are the system inputs linked to real-time sensors?
So if there is any in real time, if there is any sensor connected, then probably we can take analog input card and read those sensor signals and get inside the target machine. So you can connect your sensors, or you can also simulate your sensor behavior.
Naga, I think this is directed to MathWorks. There's a question on, can we use campus-wide licenses with Speedgoat machine?
Yes, you could use a campus-wide license. If your campus-wide is a full suite license, then yes, you have access to the Simulink real-time and all the other tools required for doing this real-time simulation. You just need to have the Speedgoat hardware.
Just one, if you can add a little more on the campus-wide licenses, because there are a lot of universities who currently are not aware of campus-wide licenses. If you could go throw a little light on that, that would help our audience.
Sure, Sharad. So MathWorks has come up with, I think a license model called as a campus-wide license, wherein we are trying to work directly with the management of the colleges and universities to provide the full suite of MATLAB licenses. So this includes all the toolboxes from MathWorks, and this will be available to all the students, all the faculties, and all the computers or laptops that are that are inside the campus. So you're not worry about purchasing one single license for each and every person or faculty or maybe a department. So it's also very easy for for all the universities to share these licenses, and all the students can make use of it. And even we have seen universities or faculties teaching all the concepts using MathWorks tools in their classroom. So that's one of the main advantage I see. But yes, I think I would encourage, if any universities are not on campus wide, please reach out to us. We'll be happy to assist you in moving to campus wide licensing.
We would love to answer all your questions, but we're running towards the end of the webinar. If we don't address your questions now, we'll come back to you. Our team will get in touch with you and answer all your queries. You will also receive a copy of this webinar to your emails, and you will always be able to view it offline. So there's one more question, which is on the inverter module. Is there any inverter module available for the motor control kit? Spurti, if you would like to take that question.
Yeah, so we have a new 2-level 3-phase inverter module available from Speedgoat. So it is having a specification where you can get individual gate driver control. And one more thing is this module is compatible with any of the FPGA cards supported by Speedgoat. So yes, there is inverter module available in order to drive your
Spurti, if you want to open the 20th slide, it talks about the 3-phase inverter. Maybe that can give more
induction motors or PMSMs for rapid control prototyping, or any of your generator.
Right, then I have one last question. The question is on BMS. How can we use this machine for BMS applications, battery management systems?
So for BMS, either you can perform hardware in the loop simulation, where you can simulate your battery cells on IO module from Speedgoat and connect your controller to the target machine. Or if you want to perform rapid control prototyping, then you can simulate your entire or control algorithms on target machine and connect to your battery paths. Yes, so you can do either Hill or RCP with our target machines.
Thank you so much to all our speakers today. In the interest of time that we are exceeding, we will have to close this session. And for all the questions we have not answered, we will definitely get back to you. Our team will get in touch with you with all the details. Thank you everyone for joining us today. Hope the session was useful. Please reach out to us. You can send an email. We will share you the contact details. If you have any further queries, or if you want to have any use case or any project that you're trying to work on, please get in touch with us. We would definitely be able to help you all with that. So thanks once again. Have a great evening. Stay safe.
Thanks so much. Bye-bye. Ciao.
Thanks a lot. Bye-bye.